Hello and welcome to the next lesson on electricity. This is electricity lesson 10 and we're going to be looking at current, charge and time. My name's Mr. Pratt, Director of Science. And for the lesson you're going to need the usual, a pen, some paper or an exercise book. You're going to need a calculator this lesson because we're going to be looking at an equation to calculate charge and current. And unless you're needing to watch this video on your mobile phone, get it out of the way, get it on silent. Try and avoid as many distractions as you can. So for your starter, which is recall, some of it from this current year and some of it from last year, I want you to add the correct units to the following quantities. I'm going to say 2 minutes, but I might give you slightly less than that. In about 30 seconds time, I'll put up the answers but in the wrong order just to help you if you're struggling. If you're slightly confused on what a unit is, it's the bit that you put after the number to say what it is that you've measured. So I'll put you that list up if you're struggling. They're not in the right order, so you'll just need to match them up. Be quick if you've not done. Just as you're finishing off, if you're in an exam and you're not quite sure if the unit starts with a capital letter or not and you want to just put the letter down, be careful because, for example, if you were to put a small j for joules, you may not get it allowed it in the exam. So either write the word out if you're not sure. It's a capital letter when it's named after somebody usually. Let's see how you've done then. So current is in amps, that's a capital A, amperes. Potential difference is volts, capital V. Resistance is in ohms, which is the Greek letter omega. Energy is in joules, capital J. Power is in watts, capital W. Length is in meters, it's just a small m. And if we do an area, it's width times height, so that gives you meters squared. We're going to be looking at a new equation that you'll need to remember. You'll need to be able to recall it and then apply it in an exam. So we'll look at fairly straightforward calculations where you're just putting numbers in, and then a bit more difficult ones where we're looking to rearrange a little bit so that we can find something different in the equation. Let's start then by trying to think about what electric current actually is. Lower down the school, you probably will have used some models to try and explain what electric current is. We use models in science to try and make our understanding a bit clearer from what's going on, because often some scientific concepts are a bit difficult to get your head around and you can't really see what's going on in a circuit because the stuff that's going on is far too small to observe directly. Your teacher might have used a water heater model or the rope model. So in the water heater model, the current is represented by the water that's flowing through the pipe. So we've got a flow. We've got a hot water pump that represents the battery, so that's pushing water around. The pump would be providing you potential difference, and that would be pumping your water around. And then when it gets to the radiator, it's got to go through the radiator, so that's providing some resistance, and then your water goes back to the pump and gets energy is pumped round again. In the rope model, the current is represented by the rope that's moving, so a flow of rope this time is the current. What's really going on inside a circuit is electrons are moving around a circuit. So electric current is like a flow of charge, just like the current in a river is the flow of the water as it's moving. In an electric current though, delocalised, so that's electrons that aren't stuck in one place, are free to move through the conductor, and each electron has got a negative charge. Electrons then go from the negative pole, and that's marked with a minus sign on your battery, and they flow around, they're pushed around by the potential difference, and they flow around to the other side. So that's what's actually going on in a circuit. But we usually talk about conventional current in circuits. So what we're doing here, we're thinking of current as being a flow from the positive side of the cell round to the negative side. When you're using the symbol for a cell there, those two lines where one line is longer than the other, the longest line represents the positive pole of the battery. So you can see in that diagram there, the current is flowing from the plus, flows round the top, through the switch, through the light bulb, and then back again. Key definition then, record this. Electric current is a flow of electrical charge. The size of the electric current is the rate of the flow of the electrical charge. So if you've got current flowing faster, there's more charge going around the circuit. So the more charge is flowing, the bigger the current is. Progress check then, 2 minutes. All I want you to do on these diagrams is to mark down the direction that the conventional current is flowing. So not electrons, so the conventional current. Just 50 seconds left. Should be finished. Right, so the first one. First one should be easy because in the first one we've got a picture of a battery there and it's got a plus at the top and minus at the bottom. So conventional current goes from the plus round the circuit to the minus. So it goes up the top, down through the bulb and back again. Remember, the current is the same everywhere in a series circuit. It can't escape. So if we've got 2 amps flowing through the switch, we've got 2 amps flowing through the bulbs, and we've got 2 amps flowing through the wires everywhere that we'd look. Second one, this time we've got the symbol for a cell. So you've got to remember which one of those lines, the big line or the little line, represents the plus. The big line is the plus, so the current's coming out of the plus, down to the bulbs, and then back up and back into the cell. Again, number 2 is the series circuit, so the current is the same everywhere. So the flow of charge, the amount of charge going around every second, is the same everywhere in that circuit. Number 3. Got to look for the big line, because the big line is the positive, so it's coming out of the big line, flowing down, and it goes all the way back to the negative side of the cell. But you'll also see, because it's a parallel circuit, we've got different branches. So the current goes along and then it can go down the first branch, the second branch, or the second branch, but then it all joins back up and goes into the negative side of the cell again. Last one, look for the big line on the battery symbol, because that's the positive. Comes out of there. Some of it goes through one bulb, some of it goes through the other, but it all goes back into the negative side of the battery. Well done if you've got that right. That's quite important. They probably wouldn't ask you to do that in an exam, but you might need it in order to do another question. So this is the big question. This is the thing we've got to get our head around. What actually is charge? We've talked about it a bit, but what is it? You will have come across it in chemistry, so we talk about a positive charge, a negative charge, or a neutral charge. Might have seen Van de Graaff generator, someone on there with a hair sticking up. So extra electrons can be added if you're on the Van de Graaff generator, so you touch the top and you're insulated from the ground. And electrons go up the belt onto the dome at the top, and because you're touching it, you get stored up with extra electrons all over the surface of your body. And those extra electrons have a negative charge, because electrons have a negative charge. So they repel each other. So there's a force between these things that have got the negative charge, and that force is repulsion. So it tries to push the hair away, so your hair sticks up. Charge then is a property of something in physics that can cause this force of attraction or repulsion. So it's a name that we've given that's causing this force. So all charges will experience a force when you place them in a magnetic field, and you'll study this further in Year 11 physics, where you'll look at electricity and magnetism, which is where this topic will follow on to. Electrons carry a negative charge then, and protons carry a positive charge. So you've got that link to chemistry there. Protons are positive, electrons are negative, and a neutron would be neutral. In an atom, you would have the same number of protons as you do electrons, so you have the same number of positive charges as you do negative charges, which means that it's neutral overall. They've cancelled out. It's not positive or negative. So we've got a new word here, and the new word is coulombs, and that's what we measure charge in. So we measure the current in amperes, amps. We measure the potential difference in volts. We measure resistance in ohms. We measure time in seconds. We measure distance in meters. So now we're measuring charge in coulombs. Charles Augustin de Coulomb, Coulomb's a place, was around from 1736 to 1806, and he was a French physicist and a military general. He did a lot of work looking at the forces between these charges, looking at static electricity and seeing how strong these forces were. So that's why we call this measurement of charge coulombs. Now there's some extraordinary numbers here. Coulomb didn't know this value. It took quite a lot of time to arrive at it because it's such a ridiculously small amount. But a single electron has got a tiny, tiny negative charge of 1.6 times 10 to the minus 19 coulombs, ridiculously small. So that's minus 0.19 no, 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 16 coulombs. In other words, a very, very small amount of coulombs. So if you wanted a whole coulomb of charge, one big coulomb, you'd need that many electrons, and I'm not reading that one out. That's a lot of electrons. So each electron carries a tiny, tiny amount of coulombs. But because there's so many electrons moving, it adds up and you end up with a lot of electrons going around your circuit to give you this coulomb of charge. So current's a flow of charge. So if we have 1 coulomb of this charge getting through that bulb every second, we'd say that's 1 ampere, 1 amp of current flowing. So an amp is 1 coulomb going past every second. So if you could put your finger on that switch and you could count the electrons going through it, each electron would add up, and then after 1 second you would have had so many electrons passing your finger that you would have had 1 amp flowing. So likewise, if we have 10 coulombs of charge flowing through this bulb every second, that'd mean it's 10 amps going around that circuit. So if we wanted, we could put that into an equation we could use. So the current is the amount of charge divided by the time. So the charge per second. Like velocity or speed is distance over time. So it's the amount of distance that you go in a set amount of time. Current is the amount of charge that gets passed in a set amount of time. Now they write it slightly different in the specification. It's a slightly different way round, but it's still the same equation. So in the specification for AQA, they say that the charge flow is the current times the time. Now we use the symbol Q for charge, we use the symbol I for current and T for time. So it's not the easiest symbols that we use, which if you can remember that an amp is 1 coulomb every second, it would help you do any calculations without really needing that equation. Some people remember the equation as never quit, Q equals IT, and that might help as long as you do know what the symbols stand for. Let's look at an example then. So I'm going to give you a minute and I want you to find how much charge has flowed through this kettle. So we've got 12 amps of current switched on for 20 seconds. And when you've calculated, don't forget your unit. There's 10 seconds left. First thing that you do then is write the equation down. So charge equals current times time, or Q equals IT. So the charge is the current, so that's 12 amps multiplied by 20 seconds. Put your numbers in. So that gives you 240. Then you add your units, coulombs, 240 coulombs. Progress check then. I'll put the equation on the top of this slide there. I want you to do all 3 of those. There's no moving around, it's simple substitution. So just be a little bit careful with number 3. There's a little bit of a trick you need to be careful of, and I'll give you 2 minutes. Just 20 seconds left. Again, check that you've got your units and your answers, and in number 3 you shouldn't be using 5 minutes because that's not what we put into the equation for time. Right, so first one, current of 1.5 amps, 90 seconds. So Q equals IT, so 1.5 amps times 90 seconds gives you 135. And remembering the unit, coulombs, 135 coulombs, that gets you 2 marks. Number 2, Q equals IT, so that's 3 amps times 70 seconds is 210 coulombs. 210 coulombs is 2 marks. Number 3 is worth an extra mark, and that's because you can't use 5 minutes. It needs converting into seconds first. So convert 5 minutes into seconds. So 5 minutes is 5 times 60 seconds. That's 300 seconds. So you do 2 amps times 300 seconds gives you 600 coulombs. So if you've got 600 coulombs, you've got 3 marks. So well done if you've done that. Now these next 3 are slightly more difficult because we're not finding the charge this time. So in the first one we're finding how long, so we're finding a time. In the second one we're finding the current, and in the third one we're finding a time again. So I'm going to give you 4 minutes altogether, and then I'll model you through the answers using the visualizer. You're halfway through at least, so practice getting on to number 3. Make sure that you're not missing off units again. let's look at the first one then. So the first thing that we're going to do is write down the equation.
Just about
so the charge Q equals current I times the time. So all I'm going to do straight away is just to put the numbers in that we know. So we know the charge in coulombs is 2000. So I'm going to write 2000 underneath there. So 2000 equals the current, and the current is 2.5 times the time, and I don't know what that is. So 2000 equals 2.5 times t. Now I can do whatever I like to an equation as long as I do it to both sides. So if I divide that side by 2.5, 2.5 divided by 2.5 is just 1, so we get 1 times t. But I've got to also divide that side by 2.5. So the time equals 2000 divided by 2.5. 2000 divided by 2.5 equals 800. So that's 800. Check what I'm looking, what have I found? I'm finding how long the time, so it's seconds, 800 seconds. Underline it to catch the examiner's eye. Second one, do it exactly the same way. Charge Q equals current I times time. Do we know the charge? Yes, we do. It's 350 coulombs, so 350 equals the current. This time I don't know the current. The current is what I'm finding. So the current times 70 seconds. So 350 equals the current times 70. I can do whatever I want to an equation as long as I do it to both sides. So if I divide that side by 70, 70 divided by 70 is 1. So current times 1 is just the current, but I've got to remember to do the same thing to the other side. So the current is 350 divided by 70. 350 divided by 70 equals 5. So my answer is 5. What is it that I've found? I found the current, so that's 5 amps. Underline it to catch the examiner's eye. Last one. Exactly the same way. Charge equals current times time. I know it's 1800 coulombs equals the current. So how long can the radio be used? So I'm finding the time, and we know that the current is 0.5 times t. And do what I like to both sides of the equation. So if I divide that by 0.5, then 0.5 divided by 0.5 is 1. So I know that t equals. Got to remember to do the same thing to the other side of the equation. Divided by 0.5. So 1800 divided by 0.5 is 3600. What have I found? I found how long, so it's a time in seconds. There we go. Each one of those with the unit will be 3 marks each. So if you nail them, you've got them spot on, give yourself a mark, and it'll be a mark out of 9.
Let's finish with a 3-4 mark exam question. I'm going to give you 2 minutes. So this one's a graph question, so you've got to get some data off the graph, and then you're going to have a calculation of charge. I'll give you 2 minutes, and then we'll have a look at the mark scheme. Halfway through your time, should be just on a part 2. just be finishing off, and there is a mark for your unit in part 2. Mark it as I go through it then. A part 1, after 0.1 seconds, so we'll find that on the bottom, the bulb works at its normal brightness. So that's the flat bit where it goes horizontal towards the end of the graph, and it asks what is the current through the bulb when it's working at its normal brightness. So the current is the y-axis, so all we've got to do is to draw a line from the flat bit and draw it across, and then be very, very careful that we're counting the squares right. So 1.5, 1.6, so that will be 1.7, don't forget the unit, and that's amps, 1.7 amps. Part 2 then, the bulb works at normal brightness for 30 seconds before it's switched off. Calculate the charge through the bulb and give the unit. So we need the equation, so charge equals current times time, and we've just found the current. If you're in a position where you've not got the first part and you need the number, so we need that 1.7, so say you couldn't do it, substitute a value in and still try it anyway, because you won't lose marks by using that number there. It'll just mark you on what you've used for the second bit, so don't be afraid to carry on even if you've not done the bit before. So Q equals I times T, so charge equals current times time, so that's 1.7 amps times 30 seconds, and then that gives us 51 coulombs. Underline your answer to attract the examiner's eye to it. So 51 coulombs will get you all 3 marks. I'm going to leave you with a summary then, so pause the video if you want to record stuff from this summary bit that you've not recorded already. I've got the key definition at the top of current, the equation that you need to recall and apply, worked example at the bottom, and the diagram of the circuit is just reminding you which way that the conventional current flows around the circuit. So that's from plus to minus, or from the big line of the cell to the little line of the cell. So well done for working on that, and I'll see you next time for the next electricity lesson.